Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Alright, first part for this problem is a little tricky. We're going to try and visualize everything that's happening here. So I have this compass because we're given compass directions for some of our quantities here. So to best visualize this, draw this on your page, the compass, north, south, east, and west. North facing up, east facing to your right, west facing to your left, and south facing down. And then lay your paper flat on your table or desk. So compasses are two-dimensional, but we're working with three-dimensional quantities here. So with your paper or your notebook laid flat on your table or desk, we have two other directions besides these four. We have out of the page, which with it flat on your desk should be straight up, and then you'll have into the page, which would be down. So this is three-dimensional. So like this, you'll have another one coming out of the page and another one going into the page. This would be up and this would be down. That's what they mean when they say the electric field is facing up. It's coming out of the page. With your paper laid flat, that would be pointing straight up. Now, we are told the magnetic field is facing south. Now, the first part here, let's start with, once again, writing down everything that we are given, everything we know. So, we have the electric field, we have E, we have the velocity for the first particle, I'm going to call velocity 1. We have the charge for the second particle that comes through, because we have two different particles that come through. That's going to be charge 2. And we have the net force for the second particle. I'm going to call that F sub net. The net force. Okay, let's do some more visualizing here. So we have that the electric field is up. So once again, lay your paper flat on your table. We're going to try to use the right-hand rule here. So we know that the velocity goes in the east direction. That would be to your right. So you want to point your thumb in that direction, to the right. Your thumb's pointing to your right. You want to point your index finger in the direction of the magnetic field, which is south, which means you have to tilt your right hand up so that your pointer finger is pointing directly at yourself. And then your middle finger points down, which is the direction of the force, which makes sense. If we have E up, the force of the electric field is up, then is the force of the electric field and the electric field itself are in the same direction, as opposed to the magnetic field where they're at 90 degrees to each other. They're perpendicular to each other. In this case, we have the magnetic field south, and with the right-hand rule, you get that the force of the magnetic field is down, which is opposite E, which is good for the first part of this problem. Once again, the right-hand rule, you have your thumb point in the direction of the velocity, which is east to the right. You have your index finger point in the direction of the magnetic field, which is to the south, which with your paper on your desk would be right back at yourself. And then you stick out your middle finger and it would be in the direction of the force, which in this case is down. All three fingers are perpendicular to each other. So we have B is down, or the force of B is down, and the force of E is up, which is good because they'll cancel. Because we're told in the first part that the particle 1, passes through unfazed. So because of that, we know that the force of the electric field E is equal to the force of the magnetic field. And we know equations for both of these. We have F sub E is equal to simply the charge of the particle times the electric field. And we know F sub B is equal to the magnetic field times charge. And you can write these in any order. It doesn't matter. They're multiplication, you can just move them around. It doesn't change any of the numbers. So you can write Q times B or B times Q. It doesn't change any of the numbers if you've seen it in a different form before. And this is times velocity. And we're told velocity is east, magnetic field is south, so they are perpendicular. So we don't need to worry about the sine of theta because it would be sine of 90 degrees, which is just 1. Now we know that the particle doesn't change its direction, which means these two forces have to be equal to each other. That's the physics of this problem, or at least of this first step, is to know that because the particle doesn't change its trajectory, the forces cancel on it. Because if you have a force passing this way, or if you have a particle moving in this direction, you have two forces acting on it, one in this direction and one in this direction. If they didn't cancel, the particle would either shoot up or shoot down, depending on which one was farther. But it doesn't do either of those. It continues in the straight trajectory it was on. It just continues on. That means both of these two forces cancel each other, which in the language of math means that we can write these two equations equal to each other. So we have Q times E, the force for the electric field, is equal to B times, I'm going to write the Q outside just so we can get rid of that because we'll have a Q on both sides. Q times B times V. And the Q cancels, which is good because we were not given charge for the first particle. Q's gone. All we're left with is E is equal to BV. So we have V1 and we have E. So now we can use both of those numbers, plug them in. You can rearrange to solve for B here by dividing both sides by V. You can get your magnetic field for this machine is equal to the electric field, which we're given, divided by the velocity of the first particle, V1, which we are also given. So now we have our B. So what do we do with it now? We want to know the velocity of the second particle that comes through, which is good because we have an equation here that involves the velocity and the magnetic field, which we just calculated here. So now we need to do some more physics for the second part. So we have Q2, we have the charge, we have the magnetic field, we do not have the velocity, that's what we're trying to find, and we don't have this force of the magnetic field. We have this net force. So the net force we can write in the language of math, which is just writing it out on your paper. The net force just means it's all the forces added together. You may have seen it in a summation form. If not, don't worry about it. This is a good introduction to summation. It's just the sum of all the forces, which in this case, this symbol just means you just add all of the F's, all of the forces, which we only have two forces in this case. We have Fe and Fb, the force of the electric field and the force of the magnetic field. Just two forces. Now, we did the physics earlier to find out what direction both of these were in. We concluded that the electric field force was pointing out of the page and the magnetic field force was into the page, directly opposing each other. Now we have a net force that's directed up, which means that the force of the electric field is stronger, but that won't matter in our final calculations. We need to find this force so we can plug it back into our equation for the magnetic field. This one. We need to find F sub B. So we have the net force, we have this. we need to find F sub E, which is a lot easier to calculate. It is simply the charge times the electric field, which the electric field hasn't changed. It stays the same for the machine. So does the magnetic field, B. So we can once again calculate the force of the electric field, F sub E. Let's do it in a different spot. That's not the continuation of this. So we'll move a little bit farther down here. We have F sub E, once again, is equal to charge times the electric field, which we have a new charge, and we are given that new charge, Q2. Q2 times the electric field, which has not changed. So we plug in that number we're given, and we multiply it by the same electric field we used in the first step. That gives us F sub E. So now we have two of the three variables here. So we want to find F sub B. So we want to rearrange this equation so we have solved for F sub B. F sub B. To do that, we have to subtract this F sub E from both sides, which gives us F net. Just going to abbreviate it as F sub n here. The net force minus the electric field force. Which we just calculated. Okay, so now we just plug those in and you have your answer for F sub B. Now we want to go back and we want to find this velocity. To do that, we plug this F sub B we just calculated back into this equation, and then we simply divide it by B times Q, which this now has become Q2, this second charge which we are given. B is the same number we used here. So once again, just rearrange the equation to solve for the velocity. V is equal to F sub B divided by the magnetic field, B, times charge Q2. And plug in those numbers, and that will give you your velocity. And there you have it.